I will continue. So what we have done, as I said, is that we have made analysis on this grid, which is a typical 10 kilovolt distribution grid. We are cooperating with a Swedish hydropower company called Vattenfall, which I will. So it's a typical grid for Sweden. This I already said. So the question was, we have studied minimum consumption and then also maximum consumption, no production, which are, let's say, the extreme cases. But then, as I said, we are assuming that that we could use the reactive support also during low wind situations. And then the question was that we are, of course, having reactive boundaries of the distributed generation because you have some kind of reactive possibilities. This is also one fundamental issue. The question is, if you have how you dimension your converter. Assume that you have a 2 megawatt wind power plant. And then you have a converter. If that converter is, the question is how that is dimensioned, because it's dimensioned, and a converter, the limits are in reality the transistors or the thyristors, depending on which type you have. But here it's transistors. So there you have. And this means, of course, that the question is how you dimension. If you dimension it that at area you cannot have any more than it's enough for the active power, then of course apply any reactive power. But normally, what I understand is that you normally over-dimension the converter a little. The question is how much, because that has an impact on the possible reactive support in maximum production. So that you have to think about when you are dimensioning your wind power plants, if it costs something extra to get an over-dimensioned converter, for example. So that is, of course, important. Then you have the on-load tap changers, and that is this one that you have here. This one, or we can call it, yes, this one, if that is controllable. Then, of course, if that is controllable, then, of course, it's easier when it's very windy. You keep down the voltage here. On the other hand, if it's not so windy, if it's very high demand, for example, then you keep up the voltage here instead. So then, of course, depends on which voltage you have here, because you have a certain capability of this one. So the question is, which voltage do you have here? Is it one? Do you always? And because the idea is that you want to keep up the voltage here, or keep it to the correct level here. But of course, in some situation, the voltage is low here, and if you then don't have this controllable transformer, then the voltage may be very low out here also for the consumers. And then, of course, you can help up the voltage using the reactive support in these ones. So there is a huge amount of parameters here, which of course influence what is the result of what you are doing. You have the on-load tap changers. You have the RX ratios of the lines, because what is happening is that if you have a dominating resistance here, then what you do with reactive power here is not have influence. I don't take this now. I will come back to that later. It has a big impact on what will happen in the system. And then, as I said, the decision of the distributed generation and the loads. As I said earlier, I talked a bit too fast. So now I should run the tutorial, but I will not. We will, in reality, I have a small program which I will show later. Unfortunately, it doesn't work yet because I have to install a thing in the computer. We plan to do that during the lunch, but so I will continue with other things instead. So the impact on the wind power, you have a huge amount of different things. Selection of power factor. I mean, which power factor should you have in the wind power plant? What is very common nowadays is that the standard today is that you only supply active power. But then there are some discussions about that you, in very high wind situations, you should start to consume some reactive power in order to keep down the voltage. I will talk a little about that. Impact on local voltage. This is, of course, that if the wind go up and down out here, then, of course, the voltage there will change. So that is, of course, one issue. Hosting capacity. That is the question, is how much wind power can we have in this grid? Or, for example, let's say we have wind power stations here. how big can the wind power station be here? That is the hosting capacity. That is one of the issues. And then the question is that which extreme cases are we dimensioning for? Then, of course, if you put in a huge amount of wind power here, on the other hand, if you can keep down the voltage in this point using this transformer here, then, of course, you can have more wind power here. But that, of course, also depends on if it's solar power there, wind power there, and wind power there, what is the demand, and so on. So there's a lot of impacts here. Impact on losses, which is, of course, an important issue, because the losses is something that costs money. You have to have production for the losses. And there is, if you have a huge amount of wind power, I can say there is a limit. I have not the equation for that, but there is a limit if you have a grid. If you produce 0.1 megawatt more, you will get 0.1 megawatt more of losses. Then you can say, why do that? That's stupid. So if the marginal losses are equal to 1, then, of course, for each extra megawatt of power production, you get 1 megawatt of more losses. Then you should not do that, because it only costs you money. So there is, but this is a very, very far up. I mean, normally you have so bad voltages at that time. But you can also have extreme systems where you have if you have dominating resistances, if you have cable networks, where in reality, because if you have cable networks, you have very low reactance. And this means that you get nearly only resistances in this. And then, of course, this means that if you produce more, you will get more, you don't get so much voltage drop, but you can, in some extreme cases, get more losses. So we have seen cases like that, but this is not in the way you normally operate it, but of course it's extremely important that don't produce only more power to create losses. That is no value. Possibility to supply the feeding grid with reactive power. That is this issue. Is what you have up there. What I have told the organizers is that I have a small Excel program I will show you later with an instruction, and that is totally free for everyone. And I have also a tutorial where the idea was I didn't know exactly how this will work. So one idea, of course, if you have your own computer, you can just download this Excel sheet and you can run a lot of small examples exactly testing all these kind of things. So that is a program that I have supplied for this course, and it's free for freely use. I have just changed 2 nodes. There is one node called Delhi and one node called Allahabad, but I will see it later. Otherwise, I use it in some other courses. Then they are not called Allahabad and Delhi. So then you have this online chapter, how good that is, and it impacts on the grid strength. The question is that here, if you are consuming a lot in this power system, the voltage is decreasing here. And that depends on the strength of this grid. Of course, if you have an extremely strong grid, the voltage here is more or less fixed. Then whatever you do out here, it doesn't matter. The grid strength is important. And then, of course, the phase angle of the strength of the grid is also important. But then also so the grid strength is important and impacts on the RX quota of the grid. That's what I said. Do you have cables? Do you have, is it a high voltage system where you have dominating X? For example, if you have 70 kilovolt or something, then you normally have dominating X. The X is normally 8 or 10 times the R. And then, of course, that is a very big difference compared to if you have low voltage where you have dominating R, or if you have a cable network. So these grids behave rather differently depending on which type of grid it is, if you have cables, overhead lines, and so on. So this is this is what I will hand out, and we will work it in the tutorial. I have a small power system grid. It's a 5 system. It's in Excel, which is nice because then it's not MATLAB, because MATLAB is extremely expensive if you work in the industry. It's nice in the universities, at least in Europe. It's very cheap. Smart company, give it free to students, and then they ask for an expensive company program when they come out in the industry. But I made it in Excel, so everyone can use it. So it's a load flow program in Excel based on optimization. And then I have an instruction for how to use the program and how to download it, because it's based on some specific things that you have to use that, and that is not yet there in the program. And then I have some small problems like this, which you can use if you want. And I will start with some of these later, but not now. Yes, this is the, here is just something about the basics. This is an extremely basic thing about wind power. Let's say we have a grid. This is a very simple case. We have the grid, and then we have an impedance out to the, so the grid, you have the grid plus an impedance depending on the strength of the grid, and then you have an impedance, and then we have the wind power out here. And it can produce active power and it can produce reactive power, and then we have a demand. This is a very simple case, just to show you a little how it works. This is conventional so-called load flow equations, and then you can, in reality, okay, we go up here again. What I know is that I know the voltage there. The question is, what is the voltage there? And then the other question is, how much reactive power can I supply here? This is a simplified model from the, where you have the wind up to the feeding point to the grid. So the question is which voltage I will get there. That is, I mean, if from a reactive support point of view, I want to be totally controllable here, and I don't want to have any problems with this one. On the other hand, if I only work with this one in order to keep the local voltage, then of course I want to keep the voltage there. So there are different issues. So the question is, what is this voltage? The question is, this voltage here, how is it depending on this active power and this reactive power here? This is a simplified, this is an extremely simple case, but if you have worked with it, you know that it's not that simple if you put up the equations. And then the question is the reactive support here. I will talk a little about that. These are the load flow equations, general for just two nodes. Very simple. This is the exact solution. And we assume that B is equal to 0. We assume that we don't consider any kind of capacitance for the lines or for the cables. We are, in all the examples I have only rather short lines, let's say 15 kilometers or something, which means that it's okay to say that B is equal to 0. There is some small impact if you have a cable of 15 kilometers, but we don't keep that. So the benefit of this one is that it's exact. It's correct. But it's extremely hard to see any kind of how it works. You can calculate things, but you don't understand, okay, if the R is changing or the X is changing, how will that affect the voltage? This is the voltage in the wind power place. So that is the drawback. Then you have, on the other hand, what we often use in power systems is that we are simplifying things. And then we can simplify it in the following way. This is the voltage drop from the feeding point to the final point, to the wind power plane. So this should not then be more than, let's say, 10% if we can accept 10% voltage drops, or 7% or whatever you have. So this is the voltage drop we have. And this can be calculated in this way, is the resistance times the active power, resistance of the lines times the active power, plus the reactance times the reactance of the line times the reactive power. This I think you have seen earlier. Here you have, and this is extremely important, that the voltage drop, if you only have P, the voltage drops depends on the size of the resistance. If you are producing, let's say, 2 megawatt in your wind power plants. So then the question is, how big is the resistance of the grid? Then the question is, assume I get a bad voltage. Okay, I get a bad voltage. Is it controllable with reactive power? Maybe. It depends on the size of the X. If the X is nearly negligible, as you have, for example, in a cable network, or if you have then if that one is negligible, you cannot do so much with the reactive power. But then you have another issue. Can I supply reactive power? If X is very small, then you can also say the following. If I have an acceptable voltage and I start to produce reactive power, then it will have a very little impact on the local voltage. I will show this in some slides. So this is not exact. This is the exact one. Very nice, but you don't understand anything. because you don't see it. But here you can really get a feeling about how it works in reality. So then you have these two issues. One is to keep the local voltage using the wind power plant, and then you can have, for example, you get more and more wind power, and then you can compensate that with reactive power. That's very nice, but then you need an X. On the other hand, if you want to supply reactive power, and you have voltage problems out here because of the P, then if you have a very low X, then it's no problem to supply a lot of X, supply a lot of Q. So here you have just this small equation, you can get a feeling about how it works. High XR quota, that is what we have in transmission grids. For example, when we have more than 70 kilovolt. I mean, if you have a 400 k, and the reason is that it's not if high voltage with transmission grid. No, the reason why we have this is that you have very thick lines when you have 70 kV or 130 or 66 that you have here. Then you normally have very thick lines, and this means that the R is very big, very small. The X is normally the same for all overhead lines, around 0.4, 0.3 ohms per kilometer. So this is rather constant for all overhead lines, but this is very different. So, and for large grids, the reason is not that the X is changing, the reason is that the R is so small. So in these grids, the XR is XR quota is larger than that. Sometimes you see RX quota, and here I call it XR quota. I think in Stefan Stankovic, who's making the paper, I think he's called it RX quota. I call it XR quota. Doesn't matter. This means that active power has comparatively low impact on the voltage, because if the R, what you see up there, then whatever the P you are doing, it doesn't matter. And this is when you analyze, for example, when you analyze, you have DC load flow, you have this kind of thing, transmission grids, then you normally say that I don't care about the R in the system because it doesn't matter, because the R is so small, and that depends on that you have so thick cables. So the active power has very low impact on the voltage. But on the other hand, that means that, of course, you can control the voltage locally using reactive power because the X is so big, comparatively. On the other hand, if you have a distribution grid, which is different, in reality, of course, you have a combination. You first have the generators, then you have a transmission grid with this relation, and then you have a distribution grid, and then you have the low voltage grid if you have solar power, for example. So you have a combination of different parts of the grid which have different XR quota. Is that what is interesting is in the final point, what is the XR quota? And that I will come back to that when we talk about solar. So the low XR quota, which you have in distribution grids, because in distribution grids you have much thinner grids, because you don't have so high currents. In distribution grids, as you hear, or lower voltage, you normally don't have so thin layers. So then you often have XR quota is equal to 1 or something. So both X and R are important. If you go down to 0.4, I mean, or 0.38, it should be here, 220 volt, then you have dominating resistances. And that means that the XR quota is very small. And this means, of course, that active power will have a big impact on the voltage in itself. On the other hand, reactive power can also be transported, because especially here, there's no problem to transport the reactive power without any impact on the voltage, because it's the distance that is the dominating part of the voltage. So this is some kind of, because a problem, what I see very often when I talk to people when you read papers, is that a huge amount of papers in the area of electric power, and when it's related to transmission systems. And in transmission system, and then they start to draw a lot of conclusions from this. But this is not valid when we come to the distribution system. And then we are talking of wind power and solar power. It's a combination of both. So the question is where you are. And so, as I said, that what we have found out, which is not so strange when you just see this small equation, is that in a cable, because in Sweden what is happening is that because of storms, we have problems in the distribution grids. So people get out of electricity just because of outages in the distribution grids. And then a lot of companies and people started to complain, and then the state said that you have to cablify more. So a huge amount of grids in Sweden have more cables nowadays than they had earlier. What is happening when you have cables is that they produce reactive power, but what they are also doing is that when you have cables, you don't have so much problems to transport the reactive power. So it becomes easier to transport reactive power from wind power to the transmission because we have more cables. It's very easy. Everything is easy when you know it, when just to see on this equation. But this is things that we are going to look more on in the tutorial. So now I will start to talk a little about solar power. But that is... I should start with this tomorrow, but I start with it a little today, and then I have to add some other things for tomorrow. Just in general, are there any questions? Because then I have to keep time at the end. How many have questions so far? 1, 2, 3. Okay, then I keep some time at the end. I stop at 5 to 12 or something. That's the idea that you are here. That's why I'm here. Otherwise, I could have just sent you this by YouTube or something. Okay, now I will start a little about solar power. From power system point, it's not that big difference. I mean, solar power, not from this point of view, not from the grid point of view. I mean, it's a source producing P and Q. Simple. And the question is, okay, they are located in different places. They are more in the, at least in Sweden today. I don't know about how in India you have a lot of solar power. Is it concentrating big plants to the transmission grid, or is it individual solar home systems, or both perhaps? Yes. I will take an example from Germany where they have really a lot of solar power. They have 40 gigawatt of solar power in Germany. So I will talk, but these lectures are a bit the same. They are slightly different. You don't have a rotating things in solar power, but from power system point, I mean, what you have at the end is the same, P and Q. So this is the same thing as earlier. Aim of the power system is to have this balance, but then we are, let's say, more here we are discussing this with realistic voltage that we need in the system. So you can call it, this is wind power, but it's the same for solar power. I mean, the general issue is the following. We have some power plants here, conventional power plants, and then we have some consumption here, and then we have some solar power here, and then the question is, here is happening things. The P is changing. Because the P is changing, the current will change here. You will get less from this one, so you will get less current here. So the wind power here is changing its production, and then you get a changed voltage here, and because of that, of course, you get a changed voltage here. This specific issue is a discussion we have in Sweden also. Because this is how it can look sometimes. You have a distribution grid or a grid like this, and then you have the production in one branch, and you have the consumption in another branch. So the question is that assume that here we can keep the voltage in a transformer or something. The question is, should we keep it up or should we keep it down? And then, of course, the wind power plant, if they want to produce, here you get a voltage increase. Normally you get a higher voltage there than here. So then from the wind power point of view, they say that keep it down. But then the consumer say, no, keep it up. So that is the challenge, how to balance the voltage you have here, but depending on the consumer and the production. We had a PhD student. He not in my school, in another school in Sweden, in Lund. He made a PhD in this area and also installed it. That he had a online tap changer transformer in this point, and then he measured the wind and he measured the voltage at the consumers, and then he controlled the online tap changers here in order to get a good voltage both for the consumers and for the producer, which of course depends on the load is changing and how the wind is changing and so on. This is of course he also installed it in reality. He was a practical power system, more this computer type. I'm only sitting like this all the days. He went out and did in the reality also. Very strange. Okay, I will start with this. This is my house. Ekerö, that is a little. Soder, which is my name, it's south in English. So it's this is my second name is south, and Ekerö, it's the island of the oaks. Okay, so there I live. It's outside Stockholm. It's the same island where the king lives in reality. He moved there first. Okay, I have a completely renewable private house. As an example, I have so-called, you know, in Sweden it's a cold country, so you need heat. But I am burning wooden pellets. I'm burning this. And then I have solar power. Here is solar power. And I have a Fronius converter. It's an Austrian converter. I will say a little about how this works, because it comes back. Now I will say a little about markets. Here you will get an insight of exactly how a rather complicated market can work. I'm not only a consumer, I'm a producer. I have hourly measurements for my consumption. This I had already before I started with production. This anyone can have in Sweden, no problem, you have the right to have it. I'm paying Nord Pool price. It's an exchange that we have in the Nordic system, where you have different prices, so-called day-ahead pricing. It's changing between every hour. I'm paying this changed price every hour, so I can be a flexible consumer if I want, but it's not changing so much. So I have different prices every hour, and I get these prices the day before already at, 1 o'clock the day before, I get the prices for the next day. So I in reality can be active on the market and change my consumption from hour to hour if I want. So that I'm paying, and then I'm paying taxes, and the taxes are in reality higher than what I'm paying for electricity. So it's totally separated. And as I said earlier, also the distribution companies in Sweden, or all consumers in Sweden, in reality all grid owners, also the transmission system operator, they own the transmission grid, they have losses, they are the biggest consumer in Sweden. The biggest consumer in Sweden is the owner of the transmission grid, because they are consuming losses. In Sweden we are 10 million people, and we have around 200 grid companies. So everyone have very small, and then we have a regulation about how they should behave. Some are private investors that are maximizing their profits. For example, the one that owns the grid that I'm connected to, they are maximizing the profit. And some parts are state-owned or owned by the municipality or something like this. Okay, so I have, for my consumption, I pay this Nord Pool price, but that's only for the consumption. Then I have one. This is the bill I get for the grid company. But then sometimes I have solar power, and sometimes the solar power is, the benefit of my solar power is that I reduce my purchase. I don't have to buy so much. But sometimes I'm selling out. But then I have to find another company that want to buy my power, because everything is measured per hours. I don't have anything called net metering at all. I buy from one company, and then I can sell to the same company or to another company. In my case, I have selected to sell to the same company. I start with that. In a year, I will change. Since I'm teaching this, I have to make it very complicated. So I'm buying from one company, and then I have a specific tariff for that. I'm selling to that company, and they pay me the same. They pay me Nord Pool price, which is the exchange price per hour. But then I also have something called green certificates, which is a way to promote the green part. So for each kilowatt hour I sell, I get the green certificate. And then we have also something in Europe which is called guarantees of origin, which is another way to market green power in general. So if you buy green power, you have to have guarantees of origin. I will not go into all these details. It's a lot of things. But anyhow, the fundamental issue is that I have one grid invoice. I have one grid company. This is totally unbundled down to the final consumers. We have a grid company and the trading company. This is the grid the company keeping the voltage. That's what I'm talking about here. They own this transmitted grid and so on. So I pay to the grid company, and that I can of course not select. This is a regulated monopoly, because this is impossible to change. So I have to pay to them, because if I don't like them, I have to move. Then this here, this is the company I buy my power from. I have in Sweden 140 different retailers to select between. I can select any one of these, and I can select hourly prices, monthly mean prices, 1 yearly fixed contract, 2-year fixed contract, green power, not green power. So I have, let's say, different combinations from different 140 suppliers. So you can just think about, just spending the time to find the best one. It says, okay, so but that is how it works. So sometimes, and then on the other hand, so there's a lot of things, and then of course the solar power I also get some kind of money for when I'm sending it. But this is the way how. So solar power, originally it seems rather simple. Okay, solar power on your panels. What do? Simple. The issue is that my grid invoice, I pay a lot. The grid companies in Sweden, they are differently regulated. Some grid companies only have a fixed tariff. You pay per month, or the maximum fuse is normally what you're paying for. Other grid companies have nearly everything per kilowatt hour. And that is, of course, a very big difference. My grid company, very good, has very high share of per kilowatt hour. Because when I'm producing myself, I don't pay so much to the grid company. If I'm in another grid where you only pay for the kilowatt, then of course, if you produce your energy, it doesn't matter. You still consume as many kilowatts as the maximum. So this can be very different, but just to say that people start to think that, to explain all these kind of things is rather difficult to explain really how it works. Okay. So what happened was that I got a new, so this is my consumption. This is how many kilowatt hours per hour. This was in January 2017. This is a measurement that I can get from my consumption. So here you see that on the, this is, yes, here on the 5th of January I consumed a lot. And then I can go in and then you can see per hour how much I consumed this hour, the 5th of January. And I will explain what this is. I got a peak there in the morning between 5 and 6. This was it's always like this. This was an extremely cold day, -10 or something. What happened was that I said that I have wooden pellets as heating. What happened was that there became some problem in the burning. And then the temperature starts to fall, and then I have backup as electric power. So then I could identify that here there was some problems. And then it was very cold. So here, at 5 o'clock, it started to consume a lot of power just because to heat my house, which is normally done in another way. And here was the peak, 7 kilowatt hours per hour. And then I woke up, and then I saw that there are some problems. So then I repaired it. It was very simple, a small thing I had to change, and then I decreased the consumption again. So this is because of the problem in my heating. And then go to the electric part. I have a converter for the solar power. I have 4.5 kilowatt panels up here. They were installed this summer. They should produce around 4,300 kilowatt hours per year. And here you see the difference. If you put up 4.5 kilowatt of solar panels, I think you will get 9,000 kilowatt hours or something in India. I assume, at least in south part of India, if it's not too much smog, I assume. But here we have a utilization time of 900 hours, so probably something, hopefully something like this. The 25 square meters, 18% efficiency. What is nice is that I get measurements. What is nice is that I get 5 minutes data. I will bring that in the afternoon. Because I have an app, I can go in and look in my app exactly how much the production is right now. I will see if I can connect the internet. This is how the production looks in Sweden. Probably not the same here. We have moving clouds. And what is interesting, and this is of course has a big impact on how solar power is working in distribution grids, at least in Sweden, we have moving clouds. And this means that you can have clear sky, and then 2 minutes later it's very black. And then after 2 minutes, it's clear sky again. And the difference in a solar power, I don't know if you know that, is that a black cloud is taking away around 95% of the radiation. So you get extremely big, extremely much more challenges compared to wind power. You never see a drop of, let's say you have 2 megawatt unit, you never see a drop from 2 megawatt down to 0.2 megawatt and then up to 2 megawatt in 5 minutes. Never. Wind is much more stable. That's what they say in Germany, that they started with solar wind power, and then some say that no, that was simple compared to solar power. But it depends on where you are in the system. But you can get extremely big changes, and here you see different days. This was a rather clear day. This is the blue one, 17 August. Here was a bit cloudy, but then it was rather stable the whole day. Then I had the next day, it was extremely cloudy. What you see here, I mean, it's the same time, or just the day after. It's an extremely big difference. And then you have here you have on the other, here was a general cloudy day. Here just happened to be some sun here. Then you have the 19th here on the other hand, it's extremely changing all the time. But this is how it looks like. An interesting thing which is good for Sweden and not for India is that solar power don't like high temperature. You get decreased efficiency at high temperatures. So Sweden is, from that point of view, rather good, because you should have very sunny and cold. That's better than at least if you have these more than silicon versions. And this is what you see here. That here this was a cloudy day, sunny day. And then you see the other day when it's not so sunny, sometimes you got more, which is interesting. I think it depends on this. I have not gone into the details, but I think the temperature impact is rather important when you come to solar power. So this is another way of drawing it. I just had it up to 12 here because I had the lecture here, I think. So I showed how it was the last day. So this is, here you see that how different it can be different days, depending on. This is, of course, a challenge when you have the voltage control. It's not, I mean, voltage control in reactive power is, I mean, that you can activate in parts of a second. But, I mean, it's changing a lot. On the other hand, if you have a lot of houses in an area, which is important, then it's not changing in the same way in all houses, because the cloud is moving all over the area. So this is some other days. Now I see it's 2 to 1. So yeah, we should have the questions now. Then I continue with this tomorrow. So now there should be questions. Should you have a microphone, or how should you handle that? I don't know. Yes.
So you showed hydro along with wind as well. So I just wanted to know, what is the role played by hydro? Is it just filling the intermittency left by wind? Is it used for some storage part as well, where wind is spilling too much?
Hydropower in Sweden is a very big resource. It currently produces 40% of Swedish energy total. So it's both for so we don't have, for example, in India, you know, you have pumped storage. We don't have any pumped storage. We don't need it, because we have so much. We have 16 gigawatt of hydropower, and then we have the neighboring. In total, Sweden plus Norway plus Finland, we have 45 gigawatt of hydropower, and the storage capability is 120 terawatt hours. So so it's both, but it's balancing and energy production.
And so I just wanted to know about the installation cost of solar in your home. So what was the installation cost, and how long it took to recover that?
For me, that's the next slide here, somewhere here. These are my costs. We have a lot in Sweden. We have since it's not so sunny as here, but we have a lot of different kind of subsidies. I get the subsidies for the investment, and I also get, I will take this more next time, but I do very short. I get a subsidy for the investment, and I also get kind of compensated tax reduction, you can say that. So I get a certain amount when for the power I export, I get some kind of certain subsidy also. If I don't export too much, that's the limit of how much I can export, but I will not come up to that level. So it's you can call it export subsidy for my power when I export to the distribution grid. Yes, that I get this. I had a 60 öre per kilowatt hour. It's stated. Yes. I mean, my let's say, okay, I can take that here also. This is the voltages. These are the voltages in my house. Three-phase voltages. I have three-phase in my house. Everyone nearly in Sweden has three-phase. So we have three-phase voltages, and they are very little depending on the solar power. The grid is so strong, and I don't know. My neighbors don't have solar power yet. I will convince them in a while. But and then, of course, then if everyone is varying in the same way. But I mean, my consumption is in reality. This was from August. I mean, this production compared to everyone that is connected to that feeder is extremely small. So it doesn't matter. My solar power doesn't matter in reality.
It is disconnected suddenly, and how the voltage is maintained.
That's
during
right.
Export condition.
That's okay. That's one of the security issues. That if I have a house that is exporting, then if it fails, then of course it can be dangerous. But then you have security systems within the. I mean, it's of course important that you can identify that now the grid is not working, so now I have to do production. But that you have.
Good afternoon, sir. As I can see that there is a large change in the irradiance, so the output voltage also getting changed from the PV panels. So are you using any maximum power point tracking technology to compensate that voltage?
You ask if I'm using any technologies to
technology.
decrease the variation?
Yeah.
No, because there is no value. Let's say that the issue is a little what I mean, what I'm paid for, because or my everything is measured per hour. You have a lot of changes within the hour. No one cares because it's not measured. And this is only measuring for myself because it's interesting to show you, to show students. But I mean, point of view, I know that in Germany, for example, you have a lot of installations of batteries, because in Germany now they have a rule for new investments that you are not allowed to export too much. You are only allowed to export, I think in some cases, only 50% of what you produce, because otherwise you can put up huge farms, wind, solar power on your house. So you are only allowed to export a certain share. But that, of course, will limit the amount of solar power that you can have. But on the other hand, if you have a battery then you can store the surplus and replace your own consumption in to another place. Because the big variation I showed you here is not hourly changes. It's changes from minute to minute. I have not yet, I have some kind of homepage because I'm selling this power, and I can go into this homepage and check how much I'm selling in reality per hour. But I have not gone into, I have not seen that yet. So okay, so that's the basics. Any more questions? No? Everything was completely clear. Yes, there was a question.
How do you maintain the grid regulation?
You should talk in that since it's recorded. That's the idea.
So how do you maintain the grid regulations and all? Do the power regulatory authorities regularly come up to you to check your power conditioning unit and all? Since you are injecting power to the grid,
Yes.
so how the grid authorities, how do you comply with their standards? How they check it?
It was like this, that the grid company, first of all, in Sweden, it's a rule that if you come with a power plant, they have to connect it. And then, of course, I have to fulfill the rules of for example, that they are, so, and there are, of course, a lot of rules about what are the requirements. For example, this, that you should disconnect when you don't have any power and so on. But otherwise, and then they change the meter, and then that's what's happening, and it's done in 3 days, and then I have the solar power producing to the grid.
Okay. On a normal day, if you talk about the distribution grids, this contains a voltage unbalance of nearly 10 to 12%.
Yes.
And since you are injecting power to the grid and power with so much variance,
Yes.
so how does the grid regulators, how they tackle such situation?
Let's
Because
say
you might be the only sole one to inject the power to the grid.
it's correct. It's just that this is very much from my point of view, but from the grid point of view, this is nothing. Because we have the demand. I mean, it's one house of 150, and a huge amount of my neighbors have electric heating. So my consumption, this variation is in the size of that 10 persons are putting out their toaster at the same time. So I mean, it's very little variation from the system point of view. It's very, from my point of view, from the solar panel, it's very much. On the other hand, if you have many solar power plants, then of course the variation will not be the same. No, I don't have a figure of that. Because the question, I have not seen so much of that, because if you have a huge, I mean, the clouds is moving, it takes time. There are studies concerning cloud movements in order to estimate how fast it's varying over a larger area. But in general, that if you see a larger area, let's say several kilometers, sometimes several kilometers, where you have a distribution area, then of course the variation will not be that big, because every house don't have exactly the same clouds over them.
Might be the variation might not be so much if you are at the starting of the distribution transformer, but if you are at the end of the distribution transformer and suppose you are having a 5 kilowatt connection, so if you are not having any solar power installed, your variation will be between 0 to 5 kilowatt.
That's right. I mean, that's correct, that if you are in the end of a very weak line, then of course you can get it. This is what I will show you later, because we have another project together with a German installation, a German company, where they have a huge amount of solar power, and then we have tried exactly to see how much solar power can you have in the end of the grid. So that
my question is same, if you are at the end of the distribution line, you will be injecting power to the grid.
Yes.
So you are already disturbing your house parameters.
Yes.
And if you are at the end, you will be disturbing other house parameters also.
Correct. And in Sweden, the regulation is the following in Sweden, that you can never, I mean, this is valid for wind power and a lot of things. The rule in Sweden, which is a grid regulation, is that if you want to be connected to the grid owner can never say no, but on the other hand, you have to pay for if there are extra costs related to that. And for wind power, it can often be that. And have a line to upgrade a transformer, so then you have the wind power owner have to pay for that. And so it should not be a cost for my neighbors just because I have solar power. But on solar power, I don't think this is not a big issue currently in Sweden at all. It's not. Any more? No? Everything was completely clear. Very good. Okay, thank you. We start again at